Hi everyone and welcome to another lecture. In the previous lecture we talked about how we can start from finite dimension and end up in infinite dimensions, and we promised that in this lecture we are going to talk about a peculiar function or a distribution that is known as the Dirac Delta distribution. So before I go and dive into the main discussion, recall that an inner product in infinite dimension was given as, let's say these functions were defined from 0 to L, then this would be just f star x g of x dx, right? And what if you had f of f, that is f conjugate inner product with f itself? This will give you f star f dx. Obviously these are functions of x, and this thing can be written as this modulus of f squared dx. This gives us the idea of a norm of a function, just like it gave us an idea of the length of a vector. So this is and in general terminology we call it a norm. So in infinite dimension this thing is kind of equivalent to that length thing that you saw, but it's not a length. The formal terminology for this is calling it a norm. So it's a norm of a function. Now what motivates us to introduce this Dirac delta function is the following. Let's say in finite dimension you had a basis vector like this, inner product with another basis vector. So this is the finite dimensional case. Finite dim dot, this means dimension case. This was denoted as delta ij, right? A Kronecker delta. In the infinite dimension, if you have, let's say, a basis x prime and you have a x, similar to this finite dimensional case, it will be given by some delta and x minus x prime. So this is the thing that is the Dirac delta distribution. There are many ways to define it. Some of the text or in literature you can define it via the Fourier transformation of the identity operation, or you can take a function that is a function g of x minus x prime, and there is obviously a delta over here, and you'll see that it is defined as pi delta squared square root over 1 of this whole thing, and then you have this exponential, and you have x minus x prime minus whole square, and here you will have a delta square. And if you take the limit, delta goes to 0 on both sides, this will end up in the delta x minus x prime. So there are many ways to define this delta distribution, and the reason we are interested in this because graphically this delta x minus x prime will denote that when x equals to x prime there is a very sharp spike. So like this, obviously it's not a very actual representation. So this is a very sharp spike when this is x prime, and all these regions the value is 0. And how does this help you? So let's say you have a function like this. Oops, sorry, let me just draw this again and let me get rid of these things. Yeah, so let me just draw the delta function again. Obviously this is not a very accurate representation, but yeah, this kind of looks similar to it. So, and let's say you have a function like this. This is some f of x, and if you integrate from, let's say, this x1 to x2, so this is your lower limit x1, this is upper limit x2, and you have this f of x, and this is also multiplied with this delta x minus x prime. Then you can see that from this graph, only at x equals to x prime this delta function is non-zero. So when x equals to x prime, delta is non-zero, and everywhere else, for example over here, let me use another color to denote it so that you can understand better. So all these regions that I'm marking with this blue color, all of these places delta is 0. So all those places, this whole integral will be 0. Obviously I need to write that dx, and what this delta function will do, that it only has a non-zero value at x prime, so it will collapse the function that is f of x into f of x prime. Simple as that. And the reason that it's happening, because this integration interval, that is the lower limit and the upper limit, are containing this x prime over here. So if you had taken this, let's say this is some x1 prime, if you just wanted to integrate f of x like from x1 prime to x2, there wouldn't be any delta function, because the delta spike is actually at x prime, and it's also known as, sometimes it's called the impulse function. Okay, let me just write it over here. This is also called the impulse function. So it's just a sudden spike, an infinite spike, but this graph is not pretty accurate because it has some width. In reality, it will have width 0 and a height of infinity, and this delta function will satisfy this thing as well. So if you have delta x minus x prime, so that means this function is non-zero at x prime, and if you have dx, this will be just 1, the number. And if you want, you can obviously separate this thing with comma as well, that is x comma x prime. Obviously the function where it is defined, this point x prime has to be included in the integration limit. For example, since your the function is defined at x prime, what you can do right now is that you can have x prime minus epsilon, and you can have x prime plus epsilon, and you can take the limit epsilon goes to 0. It really doesn't matter, this limit over here. So if you have a delta function like this, this is your x prime, this is x prime minus epsilon, and this is x prime plus epsilon. And now you might ask me, okay, why am I bothering with this delta function, right? Because let's say you have a function, a vector in infinite dimensional space, and you want to get the function out of this by writing as this, right? This thing. And now if you decided that I want to use another basis instead of the x basis, I want to use the x prime basis. So I'm not writing the limit explicitly, and this means that it is well understood that I'm only working with the limits within which this function, that is this projection of this vector f, is well defined. So what I'm going to do now is that I'm going to introduce the completeness relation. So this will be written as x prime over here, because this x I f is the same thing as x of f. This is the identity operation, and instead of the identity operation, I'm now introducing the completeness relation, that is x prime, x prime, x prime, and x prime, and this will be x, right? And I was calling this thing as f of x, and I want to see it whether this representation is unique or not. So if you just right now, since these two are bases and they will give me a delta x minus x prime, and obviously the integration is over del x prime, you can see that this is just using the previous result over here, that is the property what happens when you integrate delta with another function. Using this, we can easily verify that this is indeed f of x. So this is the advantage of using delta function, and obviously there will be many other cases that you will see this. And before we finish off for today, we want to see another peculiar thing about these delta functions, that the derivative of this delta function. So let me just write it down. So this delta function, let's say I'm denoting delta prime with this thing, that is the derivative of this delta function with respect to the x, and this will just be dd of x minus x prime, right? But what happens when you evaluate this expression? If you evaluate this expression, this will turn out to be minus dd of x prime delta of x minus x prime. And this is a pretty peculiar property of this delta function, and this can be easily verified from this definition we wrote over here. That is the very definition of the delta function. When delta, using this definition or any other definition of the delta function that you might be familiar with, that is defined by an integral or this Gaussian model that we wrote down over here, and this is in fact a Gaussian model. So these are some peculiar things about these delta functions, and yeah, this will be it for today. And before I finish off, again I want to emphasize that this delta function is pretty important when you deal with manipulations in infinite dimensions, because in some cases you might have to invoke this completeness relation. From there you might get some delta function, and it's pretty important to know that how these delta functions are combined with integrals and how they help us to calculate some stuff out of there. So this will be it for today, and I'll see you guys in the next lecture. Thank you.